Thank you for returning. In our last lesson, in the chapter on materials, we talked about magnetic properties of material, especially those materials that are paramagnetic, that is, will respond to a magnetic field, that is, a magnet will stick to them, and those materials that are ferromagnetic, or in other words, are permanent magnets themselves. We also talked about semiconductors made from silicon, which is a poor conductor itself, but can be doped in two ways. One is called N-type doping, and the other is called P-type doping. With N-type doping, phosphorus has been substituted for silicon in certain positions, and this leads to mobile electrons. In P-type doping, aluminum or boron is substituted for silicon, and these lead to electron holes. So if N-type silicon wafers are stacked next to P-type silicon wafers, electrons can only flow from the N-type to the P-type. That is, unidirectional flow of electrons. This leads then to a diode which can act as a gate for electrical current. And then transistors can be constructed from diodes, and transistors allow the rectification of electric current, that is, converting AC to DC, and the control of current and amplification of current. And we saw that these transistors are becoming smaller and smaller and smaller, so that thousands can be placed on a single microchip. We then talked about information storage devices, which could be either magnetic or optical or solid state. The magnetic storage devices utilize the magnetization of microscopic regions on some type of disk, like the hard disk of a computer. Solid-state storage devices, such as a USB flash drive, involve transistors as electronic switches, with electrons being on one side of a transistor versus another side of the transistor. And in both magnetic storage devices and solid-state storage devices, essentially we have a means of storing information in a binary manner. Either the magnetization is up or down, or the electrons are on one side or the other of a transistor interface. And this will be the basis for information storage and manipulation that will be the subject of this lesson on information science. Now, information science in one sense may seem like a tangential topic because the chapter is on material science, but as we saw, the basic mechanism that enables the storage and manipulation of information involves these properties of material, either the ability to be magnetized or to have electrons be on one side or the other of an interface between two semiconductors. So that is the connection between material science and information science. As you know, I like to step back and take the long view when considering a topic. So let's think about information from antiquity, from ancient times on. In ancient times, information was first transmitted orally. Then we also have examples where information was stored by drawing on caves. We have cave drawings. And then in the Stone Age, man developed something that was the early writing using papyrus. Now, papyrus is a paper-like substance made from the pith of a papyrus plant, pressing it into something that looks like paper. And then they used various materials as inks, which could have been soot, rust, or even perhaps blood, or other natural dyes to make markings on this papyrus. And then later, parchment scrolls were used for writing and storing information, and these were very cumbersome and very difficult to reproduce. And the great breakthrough was in 1450 when Gutenberg invented the printing press, and that then enabled the printing and reproduction of books, or in other words, the transmission of information. Now, we're going to give a very brief overview in this section of bits, bytes, and the binary code. Now, we won't go in great detail. You would have to take courses in computer science to learn more, but I think it's useful for everyone to know a little bit about what is meant, a little bit, I guess that was a pun, a little bit about bits and bytes and the binary code and how that is used to store information. So what is a bit and what is a byte? Bit refers to a binary digit. A binary digit which could be either a yes, no, up, down, or the electrons being on one side or the other of a diode interface. Okay, so that's why the materials enable the storage of information. So let's give an example. If you had one transistor, it could code for only 2 English letters. That is, if the electrons were on one side of the transistor interface or the other, it could be either on or off. This could represent either an A if this transistor switch is on, or B if the transistor switch is off. Well, clearly we have more letters in our English alphabet than A and B. Well, if you had 2 transistors working together, you could represent 4 different English letters. And I show you this little example of arrows being both up, both down, or the 2 different combinations of up, down. If you had 3 transistors working together, you could code for 8 letters. And if you keep expanding on this number of transistors, you see that when you get to 8, if you had 8 transistors working together, you could code for 256 different characters, different letters of an alphabet. Now we have 26 letters in our alphabet, so 256 is obviously sufficient, but we also have upper and lower cases and punctuation marks and numbers. And when you add all these together, we have about 228 characters that need to be represented for the English language plus the numbers that we use. This matches nicely with the array of 8 transistors, which then allows 256 different configurations. So the 8 bits of information, or an arrangement of 8 transistors together, is called a byte. And at the top of the slide I show what we mean by bit, and 8 together are a byte. So let's consider this. If you had a 6-letter word, which is about the average length of a word in an English language, you would need 6 of these 8-bit pieces, or 6 bytes. If you had 500 words of text, say on a page of a book, this would require 500 times 48, 2,400 bits, or what we say is equal to 2.4 kilobytes. Now if you have a 300-page book, you can keep multiplying this up. You would have 300 pages times the 2.4 kilobytes per page. That would be equal to 720 kilobytes, or what we sometimes refer to as 0.72 megabytes. So 720 kilobytes might be the amount of information needed to store an entire book. If you had a 1,000,000-volume library, which our library is over 1 million at our university, this would require 720 gigabytes. You're probably a little bit familiar with the prefixes M for mega, which is 1,000,000, G for giga, which is 10 to the 9th, and also you may hear about tera, which is 10 to the 12th. Well, very recently, flash drives have been released that can hold on the order of a terabyte. So you can see that we're at a point in history where all the information in a library, such as our library, could potentially be stored on one of these new flash drives. Now, computers also have a central processing unit, which you've heard about, a CPU, which is a set of transistors on a microchip. And a CPU retrieves and stores data onto the storage media. Now, a way to describe the rapidity of the development of the speed of computer processing and the ability to store information is sometimes discussed in terms of what is called Moore's Law. Now, Moore's Law was a prediction that computing power would double every 2 years. Actually, it's been doubling about every 18 months since about 1970 on, due to improvements in microchips, and transistors and diodes have become ever and ever smaller. And they become smaller due to a field that we call nanotechnology, which is the fabrication of nanoscopic, extremely small devices based on the arrangements of molecules on the nanoscopic scale, the nanometer scale. And the latest computers require only about 1 million atoms to store a bit of data, either electronically or magnetically. So again, this graph shows different hallmarks of different processors and how they are increasing in essentially an exponential manner between 1970 and the present date. In the field of information science, there is also consideration of a question raised by a person named Alan Turing back in 1950. Alan Turing was one of the leading developers of the field of information science, and he posed a very interesting question. His question was, can a computer be built that thinks? Can a computer have intelligence? Now, of course, part of the problem in answering this is how do you define intelligence? Well, Alan Turing posed a test, and that test is whether or not a computer and a computer program could be developed that would fool an interrogator from knowing whether or not it was a computer or a real person that he or she was having a conversation with. The bottom right of this slide shows the Turing Test arrangement. Imagine having two rooms separated by a wall. On one side you have the interrogator or the evaluator labeled as C, and on the other side you have either a computer or you have another human being. And the question is, can the evaluator, person C, carry on a conversation with whatever it is or whoever it is on the other side of the wall and be able to distinguish whether or not he or she was talking to a human being or a computer? So this has long been called the Turing Test of artificial intelligence of computers. And I happen to notice this story on the web. Supercomputer passes the Turing Test in the United Kingdom in June of 2014. And it says, a supercomputer has duped humans into thinking it was a 13-year-old boy to become the first machine to pass the Turing Test. I thought it was interesting, and you can read a little bit further. Passing the Turing Test means that 30% of the time the evaluator is fooled into thinking that he or she is talking to a human. It's interesting that the computer program had a name as Eugene Gustman, fooled 33% of the evaluators. Another fascinating topic in information science is the concept of the technological singularity. That is the idea that at some point in the future, perhaps not too distant, artificial intelligence will have progressed to the point greater than human intelligence, and that this would radically change civilization. The idea is when this happens, maybe it's time for we humans to pack it in. Because maybe at that point the machines could design themselves. This was the topic of a Time magazine story in 2011, which showed this timeline of information science, computer science, and the developments through the ages, and the prediction that by about 2015 computers would surpass the brain power of a mouse, okay, but that in 2023 they would surpass the brain power of humans, and by the year 2045 computers would surpass the combined brain power of the human populace. I think I will be retired by that time at least, so you guys have to learn more to keep ahead of those computers. By the way, you may recall a couple of years ago the computer program Watson playing Jeopardy against the two best champions of Jeopardy in recent years, and Watson beat them. Things to think about. We're going to pause now for another little quiz and exercise and come back. Okay?